Qua che dici, come va?
Ok, andiamo alla diretta.
Solo che abbiamo l'intro ancora. Fa intanto 4 minuti. Prega di spegnerci, lo spettacolo sta più insieme. Allacciateci il silenzio. Il vostro segnale potrebbe disturbare i nostri strumenti. Dovessimo cadere è colpa vostra. Le uscite sono lì e basta.
Quindi noi la faccia di scorsa non la vediamo più.
Sì, come parla appare lì. Un minuto. Se lui parla nelle casse ha il ritorno e sente se stesso, è fastidioso. Quando vuoi ci sei.
Good morning everybody. Welcome to the first session in the last day. And it's my pleasure to introduce Professor Martin Stoll from the University of Chemnitz, that today will present talk about the Euler solvers for fractional equations in simulation and optimization. Thank you, Martin.
Well, thank you for the kind invitation. I wish, of course, that I could be with you in Rome at this stage. I'm sure everyone is in a good mood after the football on the weekend. So this would have been a great week to meet in person and to enjoy some good food and wine. I have to also admit that for me this is a bit of parallel in time workshop, since all my other duties, this is the downside of these online conferences, that still the kids need to be brought to kindergarten. I still have lectures and all this stuff, so I could not follow everything. So I apologize if I wasn't attending your talk. Okay, and also I have to admit that some of my work here is a bit dated by now, but I'm very happy to present it anyways. So you see here a list of my collaborators. So the first work that I've been doing on this, well, the story is kind of funny. So my wife actually pointed me at fractional differential equations, and the first code I saw on the web was doing the right thing, but in a very inefficient way. So I was thinking I could do this stuff better, and with the help of Valeria, I assume everyone knows her, she's in Bologna, and Tobias Breiten, we were able to kind of start our initial work, and then in a slightly different setup with John Pearson, Sergei Dolgov, and Dmrg Method, we were able to kind of focus on the optimization or inverse problem related to this. I will point to those two papers at the end of my talk. I also would like to point out that the codes for those should be available from my webpage. So if you want to play with this, I'm sure everyone here has a code that does fractional differential equations, but if not, you can play with our stuff if you would like. Okay, so I know I'm preaching to the converted, so I go rather quickly on this slide. So when I entered this field, I was kind of surprised to see that there are kind of so many competing definitions. And I guess Valeria told me, maybe someone could correct me, that Caputo was a professor at Bologna. Is that correct? Or someone will point this out
Spento il
towards the end
microfono,
of the
quindi non ci
lecture, I'm sure.
sente.
So I then learned about the Caputo derivative that we mainly will use for the time, fractional time derivative. And then I learned about the Riemann-Liouville derivative, and that we will mainly employ this in the symmetrized version, in the symmetric Ries derivative of order alpha, let's say. I think later I might also call the spatial derivative will have order beta, and the time derivative will have order alpha. So I'm no expert on the analysis of these problems. What I claim to try to be an expert on is to solve discretized equations. And this was actually very, very interesting. And we try to look at these problems in a kind of, let's say, increased level of algebraic difficulty. So we start off with like the easiest problem, that is, we just have a time derivative, just the old normal, just du by dt. And then the symmetric Ries derivative is what we see here, comes in for the spatial dimension. So this is essentially a rather simple problem from our perspective, from the algebraic side. And then, of course, we wanted to make things a little bit more difficult. So then we kind of slowly cranked up the pressure on our problems, and we said, okay, let's consider the spatial derivative to be still our old friend, the symmetric Ries derivative, and then in the time domain, we now go over to Caputo derivatives. And since this, once we were able to kind of find a suitable way of tackling these type of problems, we said, oh, come on, let's crank up the pressure one more. And so we switched from having a one-dimensional spatial variable u to having two spatial dimensions. So we now live in an x and y world. And our time derivative is again just our old du by dt, right? So you do some type of implicit Euler, whatever you like. And then the spatial derivative, we now have two parameters. They are now beta 1 and beta 2, and we wanted to solve those. And then again, right, you see a pattern here. Why not switch to the Caputo derivative in time? And actually, we also have a fifth problem where we now then do 3 spatial dimensions. So our domain for now is the unit cube. We have 0 to t time interval, and we set 0 initial and 0 delay conditions. And the right-hand side, f is chosen. They're usually kind of, I randomly picked something that I thought would give nice pictures. So when I learned about this, and I know there has been a huge development on, let's say, finite element methods for these type of equations. So what intrigued me was these Grünwald-Letnikov finite difference approaches. And what you end up with is essentially, for me, the crucial bit down here are these matrices. And they are in a very particular form, which we've seen many times over. They are Toeplitz matrices. And I have to admit, I mean, many of you might know. So TU Chemnitz used to be a Toeplitz hotspot, and I never learned about Toeplitz matrices here at TU Chemnitz, where I was a student. So when I run into these problems, I was, I think, looking up Gilstrang's lectures at MIT to learn about Toeplitz and circular matrices, which then was a good starting point to learn some more. And I do have, if I find it, you see, I have this book still in reach, and Michael is the next speaker, right? So unfortunately, I cannot get it signed virtually. So yes, I learned about Toeplitz matrices, and it's really interesting that we have them here from my algebraic viewpoint, right? And if you turn then to the first problem, right, we see that our, so this is the derivative for the problem 1, where we discretize the spatial dimension using these finite differences. And then you have to still discretize the time. And for this, we simply relied on an implicit Euler discretization. So you here obtain the identity matrix, of course, from this implicit Euler. Then we have tau as being the time step that arises from the discretization of du by dt. And then we put all the other stuff to the right-hand side. I think this f should have an index n, but that's also not very, that's not interesting here. So what we then see is we have essentially just the linear system. And the linear system now has interesting structure. We have the identity, and then we have the matrix L beta, and L beta is now just, it's a symmetric dense Toeplitz matrix. Right, so this has been, you know, you go, and we pull this book out again, you go to this beautiful book, and you find many, many suitable approaches. So I will talk about the solution strategy for this as we go along. So here the Krylov, the low rank structure was not something that we really focused on, but we thought for completeness sake this would also be interesting. So what happens now if we go to the discretization of problem number 2? We see now we have the Caputo derivative in time, and we have the symmetric Ries derivative here for the spatial dimension. And what you see then is, if you can write this down, and we might know this from the 2D Laplacian on just the unit cube, that what we end up with is this really beautiful Kronecker structure. So what do we have? We essentially have the discretization in time by Caputo, that's a Toeplitz matrix here. Kronecker, the identity, so the nx is just to indicate the spatial dimension, minus then the identity in the time domain, Kronecker, the symmetric Ries representation in the temporal domain. Where now this is a Toeplitz matrix, the T is a Toeplitz matrix, and the L is a Toeplitz matrix. So this is a really interesting problem. This is essentially my starting point, or was my starting point for fractional differential equations. So then I guess here I'm, in Germany we say carrying holes to Athens. I know everyone is familiar with this. Let me say it anyways. So I then learned how to deal efficiently to live in the Toeplitz world, right? You have to be weak because those matrices are dense, and you never want to, you only want to keep them in your head, right? Never as a matrix. So we then realized, I just learned, right, that we can do everything using the FFT. So once you realize that you can take your Toeplitz matrix and you can take the matrix and you embed it into a larger matrix, a circular matrix, then you see you can do everything you doing FFTs, right? And this is very beautiful. So essentially the codes that I produced with Valeria and Tobias, they work in a matrix-free way because we never ever assemble a matrix because you only care about the structure of the Toeplitz matrix, right? So for our spatial, so the one-dimensional problem, I mean, I have to admit I was fairly lazy and I just said, okay, what's the first preconditioner that comes to mind? And this was a strength type preconditioner of the Toeplitz matrix. So what we do is essentially you just create a circular approximation of the Toeplitz matrix. And again, everything can be done using the FFT. And we were interested in how does this perform, right? So this was our linear system. So we have identity plus a Toeplitz matrix. And we then, like, what do you know, right? If the matrix is symmetric and if it's positive definite, then you solve something using conjugate gradients, right? So this is what I did. I just did the preconditioned CG. We found a bit of analysis that we can do. I think this is just adjusting to what we wanted to do, that the eigenvalues of this matrix here are then contained in this interval. And you see this is strongly dependent on H, which is the message to me that pays my bills is that you need preconditioning, okay? So we implemented this all in matrix-free way, just having to do FFTs, right? And also our preconditioner, of course. Then we saw that we can get some beautiful pictures where, you know, this was my entry point into this world. What actually would be the difference if you apply just our kind of old school diffusion versus doing something very similar with a different type, and we see that the solid figure was, for me, this was the beta equal to 2, and then I picked 0.7 just to see what would actually happen. The more interesting picture is, of course, this one is what happens if we crank up the degrees of freedom, right? So I wanted to see how does this scale. I think we always use average PCG iterations for 10 time steps, and we see that if I pick beta at random, at 1.3 or at 1.7, then we see I crank up the spatial dimension, always doubling the number of spatial degrees of freedom, and see that the iteration numbers stay constant, right? We have 666, and even here, I mean, to me, that's constant, right? And if it was in the one-digit numbers, I never bothered to look beyond the strength preconditioning. I was happy with these numbers, so we never try to improve the one-dimensional preconditioner further because it seems to scale so well for what we wanted to try to achieve. I'm sure there have been, and I've seen many improvements, but we were kind of happy with this, right? You sometimes see kind of the perfect scaling, but then again, averaging over time steps was then a little difficult to see that we wanted things to, you know, if the matrix dimension doubles, you see something like a doubling in the time. You see this here from 3.6 to, let's say, roughly 7. That's roughly doubling the time to solve such systems, okay? I don't know why in some cases the timing seems very similar. This might be some odd effects coming in that I'm not sure I know why this happens. But here comes the more interesting case. I mean, this is, we now obtain in the fractional space and fractional time case, we obtain essentially this Kronecker structure, which if you work with Valeria or you were like I was in a group in Magdeburg of Peter Renner, then everything becomes a matrix equation. And so we realized, hang on, this is some type of generalized Sylvester equation. And there's a zoo of methods, and the zoo of methods essentially is based on the following fact, or what I like is, I can view this U, this is what we usually do, right? We view the U here as a long vector, right? This is what I was trained in numerical linear algebra, but I can also view this as the vectorization of a matrix U. And the matrix U, of course, we know any matrix has a singular value decomposition, right? So I look at the matrix U, and what this one does is it has vectors of length this should be an NT here in the last one, I apologize. We have the length of the spatial dimension, and we have NT of such steps, right? So this is an NX by NT matrix, and we can perform a singular value decomposition of this, and ideally we can construct a method that starts off with something low rank and then never goes to the full rank problem. So why is that interesting? So let me switch to the other side where we have just our old school Laplacian. And you might remember that if I discretize the 2D Laplacian, I end up with something like this. I have identity Kronecker 1D Laplacian plus 1D Laplacian Kronecker identity. Right? This is how we construct in a finite difference discretization, how we construct our stiffness matrix. Oh, here, I apologize. There's some, so here now, please see that this was a MATLAB command, a LaTeX command that goes wrong. I now view the vector x as the vectorization of a matrix x, and the vector b as a vectorization of a matrix b, and I assume that my right-hand side, so the forcing term in my PDE has no rank, right? It doesn't need to be rank 1 like here, but it can have different. Then I want to maintain the low rankness of my solution matrix throughout the iteration, where this x tilde, that is tall and skinny times short and fat, approximates my proper solution x, based on the properties of the operator A and the right-hand side B. And then I can do a low-rank Krylov method that implies that my system matrix has this structure, and I can what does Krylov solvers do? Like CG and INRES and whatever, what they do in one iteration, they multiply by the system matrix, right? Even non-Krylov methods, like the old stationary iterations and whatever, you multiply with the system matrix once. And if you start with something low rank, you can maintain the low rank. Oh, I apologize, this is terrible here. So this was the macro going wrong. So this formula doesn't make sense as it's, we can essentially maintain the matrix, the low rankness of the initial approximation throughout the iteration. I don't know what went wrong. So what happens here is that maybe this is the better line here, that doing one matrix vector product with this matrix curly A will essentially result in a twice as skinny, it's not skinny, but two skinny matrices glued together. And this will be the same for the left factor of your SVD and the right factor. And then you can control this rank increase by doing something like a truncated SVD. So let me show you a picture. This is just, again, plain old 2D Laplacian. So what you see on the left is the CG residual going down as I have the iterations increase. And then I computed with the backslash. This is the rank. The pink line is the rank of the proper solution, right? The matrix X, that is the solution of my PDE on the 2D domain, has rank, let's say 14 or 13, right? And the red curve is the rank of my approximate solution throughout the iterations. So I start with something that's low rank, right? In iteration 10, I am at rank 13. Then in iteration 20, I'm maybe at rank 17. I go up all the way until 20, and right, I'm now here on the left. I'm somewhere here, and now my solution converges, and eventually I hit the proper rank. So the solution here will have, even though the mesh is rather large, this will be a rank 13 matrix. Now I crank up I refine my mesh, uniform mesh refinement. You see on the left, nothing changes. We still converge rather rapidly. 40 iterations. This might even be without preconditioning, I don't remember. And the rank on the right, the rank of the solution, maybe it's 12 now. Let's say it's the same. And again, my rank of the approximation shoots up to 20 and then goes back down to 13. So again, now the proper dimension might be 2000 by 2000, but what this on the right tells me, well, you only need at most 20 of those columns of dimension 2000 and another 20 of those rows of dimension 2000. So rather than storing a 2000 by 2000 dense matrix, we store 40 vectors of dimension 2000. And again, I increase the mesh once more and we see the same happens. The rank is fairly constant. Well, it's constant at 12, and the rank for the approximate solution goes up, but then eventually goes back down. Okay, so low rank methods do make a lot of sense. So, and then I had to use Valeria as a method called kpic that we used, and kpic can be used for these type of Sylvester equations. And what you want to do there is you essentially do an SVD-like approximation of your solution matrix. And it's crucial to choose the left subspace and the right subspace W in a very smart way. And for that, I had Valeria. So this is constructed using these type of Krylov methods with certain shifts, right? And what you see is you need to invert with the matrix A, and you need to invert or approximately solve with the matrix B. So let's go back to well, other methods would be the ADI. So this is maybe what comes out of Magdeburg. There's the sine function iteration, and what I focused on was Lorer and Krylov solvers. But the best preconditioners are, well, it's a little question. So we then did Valeria's approach. I added an I to it because I wanted to do the iterations inexactly. So let me go back once. So in our case, this A is a tuplets matrix and this B is a tuplets matrix. So this space is constructed inverting tuplets matrices, or just approximately solving with them, right? This is why we call it I-kpic for inexact kpic. And then we see that we refined the dimensionality in time going to 8,000, in space going to 8,000, and we have just a bunch of setups, beta like that and beta like that in the low rank BiCG. And here we have a low rank Valeria's kpic. And we see the iterations in BiCG are fairly small, but the timings were kind of not, we were not quite happy with the timings. Whereas if I go to Valeria's code, we had like, here's the number of iterations, so this is like roughly 10 iterations in all setups, and we and the numbers below just give the average number of matrix products with the tuplets matrices and preconditioner inverses or applications of the preconditioner, also FFTs of course. And we see that here the time for this large system, because you have to do Kronecker this times this, so it means like 8,000 by 8 times 8,000, whatever that is. We do this in 20 seconds. So this was rather convincing. And then we tried this. You get the same setup with an implicit Euler discretization of the 2D space discretization. And we see we could do the same. We increased the spatial dimensions like that. And we see that the low rank actually, maybe we should keep that in mind, right? Here, essentially, we refined the mesh a couple of times, right? But the timings are essentially just...
Okay, just 3 minutes.
I'm sure I managed that. Yeah, so the timings stay rather low. We could then enter the tensor world because we see, oh, hang on a second, our matrices do have a lot of structure if we add more spatial dimensions, right? And this is where my friend Sergey comes in, and we use the tensor train toolbox. And in our first approach, we just used what they call the Dmrg method, and we see now we have this dimensionality, 1,000 by 1,000 by 1,000, and we see with this out-of-the-box stuff, we get very low number of iterations. And the memory that we require is essentially, you see, our memory requirements are 9 orders of magnitude lower than what we see here. Yes. So let me just briefly talk about the inverse problem. It's the same setup. We do have now an objective function. You've seen this in John's talk. We want to bring something close to the solution y close to yb, and having a cost term here involved. With some constraint, this could be just this 2-dimensional time and space. It could also, we also did this 3-dimension. What you obtain then is you obtain a Lagrangian function and a saddle point system. And this saddle point system, each block here has a lot of structure. Everything is tuplets, everything is full of Kronecker products. And we could get away, you see that we had this is the computed state and the desired state. We do see some differences here. And then we have controls. So we do see that our method actually performs quite well. And here's how the control acts. And this is a slightly different setup if we crank up this regularization parameter or crank it down. And we see that since I'm running out of time anyways, we can do all of this in this tensor world. The code for that is available, so the paper here appeared. Essentially, they appear in the same year, even though I think Valeria, Toby, and I submitted the first version of this probably 3 years earlier. And this was rather quick in the publication process. So, but for both of these methods, the codes are available on my web page. You don't need a lot of extra stuff here. You need the TensorTrain toolbox. Yeah, and so John talked a little bit about this, but this was really able to solve three-dimensional control problems in no time, let's say. Okay. So thank you for your attention, and I'm happy to take any questions.
Thank you very much, Martin. Do you hear me? Yeah.
I can hear you, yes.
Great. So thanks a lot for the nice talk, and if there are questions present.
I can't see the chat in this full screen mode, so if there's a question, could someone please read that out to me?
You have a question?
Hi Martin, thank you for the talk. And I was curious about the sample version on your problem. And when you are considering also time. So are you considering another quant problem? So that's why you get 3 or 4 dimensional, or you simply have more special dimension?
Well, we consider all at once. So, I mean, we essentially frame everything, the whole control problem. We do discretize the spatial dimension, put into one linear system, and then this, if this is just the normal derivative in time, you do an implicit Euler, but then the spatial dimensions are kind of 3 dimensions, and they also have these Kronecker product structure. So yes, we formulate everything into a very large tensor system. And then Sergey has written this almond block solve, I think we used in the TensorTrain toolbox that we could apply, and they are essentially there's this QTT format, which allows additional tricks if the matrices are tuplets or circular. I don't remember all the details that Sergey used to get this to work, but everything goes into one system, all spatial and temporal dimensions. Does this answer your question?
Yeah. So this means that your solution stays, let's say, low rank, or in a low rank vector format for all the text steps, something like that.
Well, I could not hear you so well, but the question is, so will the solution be low rank? I would say in the forward simulation, maybe not. Especially if you have something that's like an advection type problem or something. But in the optimization problem, you usually want to bring the solution close to something boring, right? You want the flow around something to be rather stable, or you want the temperature to be rather stable. And that, I assume, is usually means low rank. And then you drive the solution to something, the desired state is supposed to be low rank, then I think there's a good reason for this to be low rank. If you just do the simulation, we've seen this with just the normal advection diffusion problems, it's not necessarily low rank, right? If you have a shock that goes through the system, then things might not be low rank, right? The worst, I mean, look at the identity. It's the worst possible low rank matrix, right?
Yeah, I was wondering whether you found some problems where some similarity comes up, or maybe in time, but and what does that mean in a not-at-once formulation?
We didn't find any problems, but I have to admit it's been a while since we kind of I have to admit after this paper we stopped investigating. Which that doesn't mean there are no problems. We just didn't encounter any on the way to this paper, and after that we haven't touched it. So there might be some, and there are still, I assume, lots of open questions. So one thing, maybe just one question that always interesting to me is nonlinearities and low rank, right? That's a big challenge. If I can give you something to work on, right?
Yeah, you're right. you very much, Martin. And any other question? We don't have questions.
No.
So, thanks again, Martin. And
Thanks for having me. I was very honored. Thank you.
thanks, Martin.
No, se di che questa sarà una presentazione privata che non andrà su YouTube.
Hello, Michael.
Yes.
You hear me? Okay.
Yes.
So this is a private presentation. There will not the YouTube channel. It's only for the conference. Okay. Thank you very much for attending our resource. And it's a pleasure to meet with and he's from the Hong Kong University. One of the experts on technical analysis. About the condition method
Thank you. Okay. First of all, for the invitation, so that I have the chance to share my research results related to the fractional differential equations. Actually, I prepared the previous speaker, Martin, and because he set up the equation and this matrices, focus matrices, and then that will be actually in my talk. That will repeat some of the themes and also the matrices. So this is the outline of my talk. So I'm interested in looking about the distribution technique. So you see in the previous talk, mentioned about Martin that many related actually have the focus on it. And this is also why I'm also getting involved in this kind of research, because this is also one of the especially my PhD thesis, talking about how to do the definition on the focus matrices. So in the outline, you see that is I will briefly discuss about some of the given the background of these fractional differential equations. And because now this is not a simple given the matrix problem, actually we are given the fractional differential equation. So that means one of the very important elements in working out what are the specific things talking about of these equations, so that we focus on the problems. And then after that, so we will see how to do it. That we work on how to do numerical solvers and also differentiation. And then the final part of my talk, I will talk something about my also recent work with also doing some inverse of problems related to the convolutional equation. So you see in the yesterday talk by Professor Dean, and also Martin talk is also touching some about the optimization involved, and also the inverse problem in general in fractional equations. And then I will have some concluding remarks. So in the I think you are familiar with all these equations in these content, because I'm so sure in the last day that you see this equation is the same fractional diffusion operator, and then this is equated fractional, sometimes the metric version. So then here the alpha is between 1 and 2. So we can see that if alpha is close to 2, that will be close to the standard of Hausen equations. But when alpha goes to 1, that will be closer to the first order equation. So somehow we need to build in some preconditioning techniques or the numerical solvers that somehow can be robust to this the range of the values of alpha in between 1 and 2. Because in terms of nature, that will be quite different. Because one is closer to first order, and another is closer to the second order. And this here is the definition of the black and white and the various derivations of this fractional diffusion. And then of course you can study the time-dependent motion and also time-dependent motion. Okay, and also mentioned four possible cases that in the margin top. So if you consider spatially and then the time dependent, you can say these are spatial fractional equations. So another thing I should highlight here is that part of my I will present the conditioning method of the Numerical Solvers. One of the I would like to say in this kind of equation, one is say for example, say fractional diffusion DI is a function of the spatial variables, or even the DI, if you have time-dependent equations, then the DI depends on both spatial variables and also time variables. So of course that will be the more difficult case. But I will see that is this DI in this fractional diffusion equation or even in time fractional equation somehow will play a key role, because I think in the yesterday's talk, Professor Jin, and also someone talking about why the future model of this fractional diffusion problem, because we find that in the medium, when you use the material go to the medium, that somehow this confusion matrix plays a key role. Somehow, because of this material inside the medium, that affects the diffusion rate. That is why the fractional order plays a role instead of the standard order in the second order. So this is also when we define the conditioning method. That's another interesting point we need to consider together. When this CI is not a constant, when this CI is involved with spatial variables or even time variables together. So I will talk more about in the next few slides. And of course, you can also consider the another type of design, like you have the fractional diffusion on the given time, CI plus CI minus on the fractional operator, CI star, CI. So we can see that there is another transition in the CI and CI minus. So the fractional some change in the visibility of and also one side equation. That also is interesting. Of course, in terms of this will be more a non-symmetric case compared to this. You will see the matrices very soon. And then that will be another time fractional differential operator that's talking about over the time. Okay, so now come to the numerical discretization. So and also corresponding linear system form. So assume that first of all we assume that on the uniform spatial partition, and then we apply this formula that is the stable and convergent formula. So approximately that is like our fractional derivative. This kind of formula is first order. It's only the first order. That means in terms of the discretization, that will be the first order approximation scheme. So and the derivation of the formula is like this. So we know that can also define the derivative in another manner. When h tends to 0, that will be another definition to consider on the integral form of this fractional derivative operator. So So you see that is actually this type of coefficient weighted on the solution on the different formula. So of course you see that now the different formula, first order and on the second order difference, they have some either 1 or minus 1 or 2 or something like that. But now here you see that the formula is somehow non-local, not just restricted to the UI and UI minus 1 and UI plus 1. You will be more larger, okay, the cover the weak points compared with the standard first order difference and also the second order difference. And this formula, I mean that the coefficient of this CK alpha can be calculated by this recursively formula. So that means you know that for this formula is how they behave. Important thing is about this formula is even this is local, but this is not just like the image processing, like you have the variation that is a constant, our focus further on the that somehow this CK alpha is a formula of some indication that. So that's also reasonable because even though this is not local, that's talking about the weak point on how to get this. And from the integral formula, we will see that why somehow this is a shifted formula but this is only the first order. So actually in my talk I also mentioned that there's also some research having what happens if we consider more high order and if you write it down just on the space fractional equation you can and suppose now you consider these two sides fractional equation. So you will get this kind of something. So because you involve the left-hand side and right-hand side, so suppose now the D is the same for both sides. So in this case, you can develop a symmetric focus matrix, and you can write out the formula what does it look like. And okay, so this is a symmetric focus matrix. So this is interesting to see because that means that when you apply this formula, you will get the structural matrix. But if the D is both sides, left-hand side derivative and right-hand side derivative, they are different, and talk about D plus D minus, then in this case the matrix is no longer symmetrical. But you can still write it down as a structural form. That will be like the D plus. Suppose D is more of a spatial vector, for example, then that will be you have a diagonal matrix, and then all the at time the T alpha, and this is about the form. Okay? And you can consider why this, because in here you have the lower triangular part. Okay? And then actually for this symmetric version is you combine both lower triangular part and upper triangular part together in order to get this symmetric. But if your D plus and D minus are different, then in this case, especially more the spatial level, then in this case you have the lower triangular matrix, T alpha here, and D minus and D minus another matrix that's talking about the spatialization, and then after another T alpha upper. And that's that will be possible. So this is why the symmetry is basically T alpha and T alpha function. So for this one, you get about symmetry matrix, but still somehow balance because you have lower triangular line and upper triangular line. And of course, you can consider one-sided equation, and in this case, you have only D times the T alpha. So you see that in this kind of equations, one thing is it's no longer focused because unless the D plus and D minus they are constant. Okay, otherwise it's no longer focus matrix because this is one of the very simple examples to demonstrate that you have a diagonal matrix and focus matrix, you will destroy the focus structure. That means that the diagonals are no longer along the diagonals are no longer constant. And so this is also another interesting point to see how it works and what kind of efficiency techniques we can apply to speed up the equation. And as I mentioned, this speed up and T minus or even even one side of the time equation, that also plays a role because why we can consider the other derivative or the two-dimensional derivative because of the medium of the distribution coefficient that somehow the matrix and the matrix the distribution becomes not in the standard. Okay, so not just the binary differentiation you can consider, you can also consider in numerical analysis other interesting schemes. For example, I also consider binary volume scheme that you assume on some rule-based function. For example, we express the binary simple linear function, and then in this case, we can use the rule-based function and then to calculate the integral. Formula, and you can get the resulting coefficient matrix into this form. So you see that is a little bit more complicated, but more or less the same structure. So you still have the say the diffusion part on the maybe left side and right side, but now you can have the focus matrix. But you have also left and right and given into this form. So one is a lower triangular part, another is like lower hazard, but still focusing matrix, and the coefficient somehow also decay. So even if it's not local, but you have this decay coefficient. That means the weight on the far away is still weighted very small, on the little points or big points here, you consider that still a high. So that's reasonable, okay? Because you different from the larger image processing. Kind of very operation. Okay. So in terms of structure, that would be a little bit complicated, but you see that there is algorithm time, so it's matrix and then for the time equation, I think in the last class, also consider this kind of first order difference in time, transition error, then you can fractional differential operator, and then using the time width, and this UI will be spatial discretization. You have the regular time and you can consider all the time, that means the time set from one time to the final time set, then you will get the corresponding coefficient matrix that will be like you can write as a tensor form because that would be the Tn conic component I and I conic component another G0 from the formula coefficient. And Tn here is just a lower triangular focus. And okay, so depending on what kind of the spatial operator you consider, general part or even you have the spatial fractional differential operator, then that will be replaced by the identity by some other matrix that corresponding to the spatial discretization. But let me give some more extension to this kind of scheme. For example, we may consider because for shifted formula so far we discussed that is by the first order spatial. But you can also extend it to a second order or even higher order also about this. So for example, that will becomes another coefficient weight on this response function. And in this case, then that will be you can define your so-called weighted shifted formula. You can see the second order form. So in subject is just a combination of the first order in the right hand. Okay, so we create this coefficient. And but the structure of the resulting coefficient matrix is the same because of this here is because we assume that I should say that why we can get the focus matrix not really. Not just because of this condition, it's just also because we consider uniform weight. Because if you consider uniform weight along the spatial dimension, then when you discretize, you will have the same formula applied to each point, so that you have a 1 over h because of the discrete size. So when you write out the whole matrix, that will become the focus matrix, and this will be recursively if you use the same weighting formula. Okay, so why this is the focus matrix here? Just like if you think about the Laplacian matrix, why you get the 2 and the -1 and the same. Okay, but you assume that one is the uniform matrix. So another aspect is for this kind of equation, when you discretize it, if you somehow know of the boundary layer or something, then that you may need to pay attention on the question. Maybe you need to use uniform weight, then in this case your total structure somehow evolves. So that will be another interesting question to consider. Okay. So depends on what kind of problem you consider. So this will be another interesting point to take together as well. So for the numerical analysis and also numerical equation. But in that case, for this second order, we can shift as the structure of the composition matrix is similar to our previous scheme. But the question is, for this scheme, if you using the first order, if you using some of the high order, say for example, I also using time and also second order together, this is the pattern scheme of time because we mentioned that this is the first order operation in time. So we also need to enhance our second order time. Well, if you do something from the analysis, in this case, how to analyze the so-called stability and also convergence and also the error that depends on the technical concept, the second order scheme and also the weighted shifted different scheme is also second order defects. This second order defects. So you can do this more analysis, not just the numerical linear. Okay, but let me focus on one of the equations back to the. If I want to solve the first order and the spatial discretization schemes, and also we have this d plus d minus, and assume that we have the time dependent problem, and this is just like single order scheme, then first order. Then you can revise the computation that but this is not only one computation. You will solve the spatial problem at each time set. So you will get this computation at each time set. So maybe in this case depends on whether d plus or d minus is time dependent, so then that will affect the computation. Okay, so that you see that this kind of a structural equation, you have a scaled identity matrix, 2 diagonal times. So now it comes to the question: if d plus and d minus somehow they are not somehow close to a quite big, then of course you can imagine this destroy your total structure. So now if you use the certain matrix like that, we do not approximation to keep our but the question is, remember this alpha is not symmetric. So even you will not using a full circle and then you approximate it by the lower part of the. So first of all, that may have some issue maybe. Another is even you can apply this certain matrix, you will have the diagonal matrix type that you ask the question is the whole precondition is no longer circle. So how you can using FFT to solve these preconditioning equations, that is also common. So that means we need to think about other possible preconditioning strategies. So in here in my talk, I will basically talk about one inverse type conditioner, another type is the more separate That means the first one is the inverse time find what's the inverse of the negative, or we can consider try to sample this beta t into second manner and then cumulative. So this is the approach that we work for in the last 3 years. Also remind that because this is not a symmetrical conversion, as long as beta and d minus they are not the same, then we need to use the DMS method to solve this symmetric. So as I mentioned, the first one, the idea is to approximate the step called E for the sum of the scalar identity matrix and 2 diagonal times 2 base matrix. So that means I need to find a way to approximate the inverse of this matrix. So what does it look like? So somehow it seems to be not easy. What is the inverse form of this matrix? So we come up with a technique saying that even though this is open, we know that we can find a certain somehow good approximation. And for certain, of course, I cannot compute beta and the certain together, the inverse, because we have these two together. So how about I do it one by one? That means I take the sample because the deepest I cannot take care of all the diagonal entries. I just take a sample on something, and then because if this is a sample and then times the certain matrix, I can take the inverse, and then take the inverse back, I can compute the corresponding rows, and then combine all these samples together. So this is actually you can see combine that row by row, and then do the inverse. So this is our idea to see how to compute the so-called approximate inverse of these matrices. And this actually learn it from also learn it from the inverse condition for the equation. Somehow know how to combine we are very efficient in the sense now we set the case by certain so that we can get the sample of these certain inverse can be very quick, and then so that we can assemble the row by row very quickly to the simulation. I think this is some of the part. And then of course we try to prove theoretically how good of this, even though this is a non-symmetric system, but we can still prove that know the difference between the conditional and also the inverse is just the lower matrix and the smaller matrix. So of course for this non-symmetric matrix is difficult to utilize the convergence rate and not the number of iterations. But we believe that this is the difference between the matrix of lower and smaller matrix. So somehow but here is we are saying that this over average time, the power alpha over delta t is somehow is a constant. Okay, it's a constant in our pool. So that means you need to cater this discretization in the spatial one and also the time one in very level manner. But this kind of approach is very open to the two-dimensional case. So that means when you consider two spatial variables. Okay, so this is the open question, but this is also true for in general social images. And here is also okay, and this is a comparison, and this is our proposed conditional, and 2 and 4 represent the number of condition points to consider the examples of this. So you expect that when 4 somehow better than time and also the spatial and state one somehow. This is an average one. Okay, that we go to solve it in every concept. When we go to 2-dimensional, we can also do it, but we can still write it down in the structure, and this is the result. So you see that now that is more integration compared to the I also do something for final volume scheme. So this is the result. We compare with the certain matrices, and this P4 and P6 refers to our idea of how many number of points. So you see the performance also pretty good. alpha for 1.9, and B and L is somehow also composed by and group on these kind of equations, type equations. B is somehow using the first order derivative, and L is using second order derivative to put in the combination. So when alpha equal to 1.9, so you said that they're close to second order difference. So you see L performs quite good. Actually, can perform quite well compared with our P4 better than. Okay. But for the first, if you're using the first order, that will not be, because you cannot capture the second order property. So you see that it's more integration. But when you go to 1.1, you find that somehow the first order difference idea is good, but the second order difference is not good. So you sometimes we would like to say our method is to try to give some more robust performance over the alpha. Okay. So another idea is comes to mind is how about instead of using the point to find out the possibility inverse, can we do something like that? Because E is actually we know that E times E is equal to and I separate that such that I can cancel addition E. But of course the question is because we are going to solve it every time step. So now how does that work? So we try to get the E out and then the total structure is another. So one of the ideas is to get the E square root and then you have another idea the identity part only the sum of the mean value of these entries and then times these resolutions. I think that here is another mean on the inverse of the identity. So somehow under some bounded diffusion condition, you can prove that this can be really only bounded by the constant and not the discretization of some time. And I can show you that this E and E are our result, and this is our this is the one E formula. So given alpha, and also you see that the S1, the first order difference and second order difference. I should point out that why you see that the first order difference may not be good, because this is a very is a non-symmetric case because you only have the one side, so you have only a line close to a lower triangular torus matrix. So you see that the performance somehow is not good enough, but we see that the number of iterations somehow quite small. Okay? And this is another technique for fixed stable size and the time, so we still get a very good constant number of iterations. And this is like a conditional number that we use for our rule. And we can also extend to the second order over, and then see the iteration and for even even here you can consider that when you go to the one side equation for the spatial x and spatial y, we have different outlet data. Another case is acceptable precondition we apply to the one side case, and we also apply to the two side case. Yes, this can be also applied, and also we can also generalize to the high order spatial discretization under the second order one, and even higher order one. And we find that the proof can be made for 1, 2, and 3 cases, assuming some of the defined distribution. And of course, the key is we need to show that the fractional operator is matching constant on the case. So somehow we need to figure out why the higher order discretization will work. And I can show you the example. Yeah, of course, in this case, it can be measured in the conditional, so that you see that it becomes less complicated, because if you have the diagonal matrix taken out, so it's simple to solving it. And the G here is you are solving a standard torus equations. Okay, then in this case you can have using the standard torus equation technique that can be circular, that can be other possible, and you can apply to all these equations. So this also has some additional advantage when you go to see. So here is we use for one case, and because we can also apply the right degree on solving the torus equation. So of course, of course, another question we are interested is how can we also extend this credit methods and the campus identity, and also how about the high order spatial scheme. So here we how we get the matrix after we doing the discretization. So now we need to make some assumption on the spatial distribution and also the scheme that we can prove the continually stable and yeah, because one of the very important is for the first order scheme and second order spatial scheme, somehow the dominant of this is but for the higher order spatial scheme, somehow this topic is not controlled. So that is why it is you can say a special difficulty to show why the scheme is not working. And so we need to build up this numerical analysis to say, for example, consider this third order or even fourth order same scheme in the same domain. So you can see that this is like we can do the different step size. You can see that this is still true in terms of this third order in spatial discretization, and second order because now we consider the credit scheme. The same for fourth order and second order. So that means the good thing is because then you can use the smaller number of the reports that you can get a very high accuracy. So that is also a way to deal with the so, but another question is about some on this work. We somehow we need to assume that the distribution coefficient. So when you go to the non-technical coefficient, that will become to be physical question, because in this case you will solve the problem step by step. That will reduce a lot of time and whatever to do this kind of equation. So we have another idea to in numerical analysis. Can we also do something like the ADI network to see how to settle, not just in terms of prediction, we also settle in terms of the spatial domain to consider how to do this non-settlable coefficient problem. So in terms of the equation, consider this kind of equation on the ADI network for the non-settlable coefficient. So yeah, this is the lie down the equation. And also another interesting thing is that because we do using this ADI network, basically you can reduce the problem, the one-dimensional problem. Then you can solve the one variables very efficiently, no matter by standard method or the separable idea or even inverse conditioning, whatever. That would be much faster. But of course, we need to prove this kind of the iteration scheme is also unconditionally stable. We can get the what is the accuracy of in terms of the spatial levels and also the second order time. So we show that it's true for different alpha, and then we see that this is still a second order, and for this one, this is also a time second. So for this second order, because for this is somehow the existing ADI network cannot have somehow you cannot directly apply that to itself for non-settlable. So usually we are using between the matrix so that we can of the contribution of this work in how to deal with the non-settlable coefficient in the ADI. And also we can reduce the computational time and get some variables. So for example, you see that for this kind of scheme, different fractional order, you have ADI, and you have one second you can have but if you using standard identical scheme that we also discussed before, then you can get almost like 1 minute or more than that. Similar, then you go to higher accuracy, and then you see that it's more hard for the standard mainly because you need to solve the equation, but here you only solve one dimension. Of course, far we talk about time-dependent setting. We also can discuss time-independent setting that is solving this equation. And this go back to the question is how to study the generating function of these matrices. Then we can show that there is somehow, if you're using the non-certain, if you're using sign transform prediction, you can get the low line and upper bound independent of the problem. So I think this is all, and this result is available for multi-dimensional case. So that means if you this also tell you that if you consider double prediction, that will be very helpful. So even if exercise using the sign transform prediction, that can be that's very good. Finally, I think in the marking part, we also talk about time-state sectional tactile equation. So the second is like the lower triangular, and then you have the spatial fractional differential equation. And so you will see that now P coming from the I, the D times I times coming from the of N. These kind of equations. So how to solve it? So we have come up with another idea instead of the certain on P, we try to use the so-called certain matrix and then to complete the whole structure. And because the epsilon is small, so this is also good for the precision and so instead of the concept of set solving equation, you can solve it all in once and then you can get much faster result. Okay, finally I come to the inverse form. Sorry, I think especially in the talk about circle setting inverse problem. I think still it is a very open problem in many areas because you can have the outer, the derivative, you have the diffusion coefficient, you have the source term, and etc. So in here, I only focus on the identification of the unknown source term, go through the medium, and then to see what happens. And yeah, in particular, the time, you have the time of the medium, and you have the fractional time control from the solution. And well, you have the additional data, is the time function to T, you have you can observe. So this unknown is about the effect, so yeah, how to do that is one of the ways to how to solve that. Even though because this problem is very simple, so in this case you need to do the factorization in order to get the level equation and get the time. So here we try to regularize all the time. Okay, I mean that time point, and you have a factorization operator, and then on this x put it together. This is so-called the four-line boundary variable method. And that is so this is F is also unknown, and also U is somehow unknown. So you can see, well, this is compared with yesterday, the simple part, this is very simple setting of the inverse form. Okay, and if you write this equation one time, then like this, E is unknown, and then F is the source term unknown, then what you get is the operation, and then this is A is like a housing operator, this is the position coming from the addition of the unspecial, then also get this. Because this is interesting, you have this structural matrix, you can consider the precondition. I don't think I need to, but you can using the L curve, and because in inverse problem, you can also study this kind of equation like in image processing. So you can using this factorization technique to study how good of the parameter effect on the solution, etc. So this is true and this is noisy, but if you do not consider the quasi-boundary method, then you will get the logic because of the noisy data in the operation. Okay, so very quickly to conclusion. So I think I can send the summary how to look at how to solve some linear system with the structural information. And I also need to do some some differential results. For some high-dimensional problem that involve the two steady variables and somehow the channel is still open. Maybe because you can imagine this kind of equation is not a this is also important because we start from the fractional differential equation instead of just the matrix. Because in terms of modeling, we need to understand why this fractional differential equation exists. And also, I think the inverse problem becomes more and more important because it validates what I consider the fractional type model. Because I need to extend people is because of the medium using the binding operation and it's much closer to the eye. And then of course definitely more for inverse problem there are many open problems in numerical solvers. So recently I think powerful technique is how to use the deep learning to new number method to solving this kind of no matter the fractional differential equation. You can also apply deep learning technique to solve the inverse problem with this. So I think all these will be very interesting. Not just the numerical linear algebra, we can also rely on the deep learning technique to form some of the interesting methodologies to solving So I stop here. Thank you very much. For this project, I think we do not study the regularization of this. I just follow one of the work that published a few years ago, which is about the identification of terms. People use the term fractional differentiation, and here the R is the regularization operator. It is a quadrature method. I think here is what they try here is also using the setting up the equation. It proves that if you somehow you can recover the F and it's a popular regularization method. That means when the noise goes to zero, then your F solution will go to the branch root of the solution. So I think this is the in regularization people will always prove this kind of the argument. Okay, so here I just using using the apartment matrix. The same as so of course you ask the question is whether we can use other regularization operator like the L1 or the other fractional differences. Well, this is again another modeling problem, but I think the fact is that with the assumption of the solver need to become higher on the top end. But if you do not have that, I think you can only measure some of the so-called regularities on the net. Then you need let's say smooth terms, then I think this apartment matrix that would be useful. But this still very open problem because for this project, for inverse problem, I think it really makes sense because I always ask myself is why are we using the fractional differential equation to do the modeling? Okay, so definitely that is some advantage because of the diffusion medium that so the inverse problem somehow is validate why this modeling actually works. So I think this is when you go to get all correct data and get the problem. Inverse problem is the key to verify why the fractional type of differential operator equation they are related to your model or the reality the operation.
Okay, so thanks again.
Thank you very much.
And thanks to the speaker and it's time for the question. Bye.
Se volete lasciare, lasciatevi. No, vabbè, nel caso qualcuno non ha avuto il certificato di partecipazione al servizio, mi manda su vabbè, io
Good morning again, and now we have the second plenary speaker of the day, Professor Van Dijk. Good morning.
Hello.
Hello. Thank you for accepting our invitation, and it's a pleasure to introduce Professor Van Dijk from Edinburgh University of Edinburgh. He's expert not only of fractional differential equations and fractional diffusion, also in many things, for example, evolutionary problems related to wave propagation, boundary equations, wave equations, and many other things. Thank you, and now we can start.
Okay, thank you very much. Thank you very much for organizing this workshop, and of course for inviting me. It's great to see so much work in this topic. So I'm just, for some reason, failing to. There it is. Okay. So. Yes, I worked on both fractional Laplacians and time fractional, but this talk will be on time fractional. So I'm presuming, since you're not stopping me, that you can see the slides and you can hear me.
Yes.
Okay, so this is joint work with my PhD student here at Harriet Katie Baker and a long-term collaborator, Maria Lopez Fernandez, who was until recently at Sapienza, but has then moved back to Malaga. And with thanks to National Physical Laboratory and the EPSRC, the funding agency in the UK that funded Katie's PhD. Okay. So let me skip the title, which in retrospect is not so great, but go straight to the content, which will explain better what I want to talk about. So let me just check the time when I'm starting. Good. On one hand, it's very simple. I really just want to talk about a fast and memory efficient computation of the Riemann-Liouville fractional integral. Okay, which here it is. So we weaken it by the convolution with this singular kernel, which we've seen many times up to now. Okay, and then I want to illustrate this with a couple of applications. So one is our kind of workhorse example of subdiffusion or diffusion wave equations, where this is a fractional derivative of order beta, where beta is between 0 and 2. And here, mostly I will use the Caputo derivative, which means that I take n classical derivatives, where n is the ceiling of beta, and then apply the above Riemann-Liouville integral of order n minus beta. And then the application that really I was interested in, and that Katie's PhD thesis is on, is an application coming from acoustics, in fact, really nonlinear acoustics, though I will only talk about the linear part, and that's here a slightly simplified form. So we have the wave operator, the D'Alembert operator, and then we have a fractional damping. So this is to model what's seen in experiments, that the attenuation of the acoustic wave as it goes through a tissue depends on a power of the frequency of the wave, but in a fractional way. Okay, so this is one of the models of this behavior. Okay, so we want to apply this fast method that we developed to these two problems. Okay, and I will just look at the linear part for what we are talking about here. The nonlinearity doesn't create any difficulties. Simply at each time step you have a nonlinear system to solve rather than linear. But the fractional part remains the same. Okay, so let's go straight in. So again, sorry for repeating this, but here it is again, the fractional integral, the Riemann-Liouville fractional integral, and this is, and I will think of it really as a convolution with this kernel K. And it will be important for us to understand its Laplace transform, and and in the Laplace domain, the action is the multiplication with the power of s, fractional power, negative fractional power of s, of the Laplace transform of the data G. Okay. We will use the Caputo fractional derivative, which then first takes the classical derivatives and then the Riemann-Liouville integral, and similar thing happens to the Laplace transform, where the Laplace transform of u gets multiplied by s to the power beta, and then if the data is not zero, there are some correction terms there. Okay. So now there are many methods to compute the fractional time derivative. The one that I will use is convolutional quadrature, going back to Christian Lubitsch's work in the 80s. Here I will give there are many ways of introducing this method. And here I'll give a brief introduction to it that will be useful for what I'll be talking about. So here's the idea, and it's general, it's not just for the fractional derivatives. So we look at the following convolution, where the k and g play a different role. G is the data, k is the known kernel. No? And we assume that we know its Laplace transform. So what we do is we replace the little k by the inverse Laplace transform of its Laplace transform. Okay. So here I write the inverse Laplace transform in the Bromwich integral form. So this is an integral along straight line parallel to the imaginary axis. Okay. And I've swapped the integrals around as well. Yeah? So I'm not justifying this at all. And in some sense it doesn't matter, because this is just, for me, a motivation to develop a numerical method. And the numerical scheme will be well defined. Okay, so I swap the integration signs. And then what I'm left with is with a k, capital K outside, and then this integral here, which I call y. And here you can recognize the variation of constants formula. Hence, this y solves this ODE. Zero initial data, and dy by dt is s times y plus g. Okay. And now, the very elegant idea of Christian's is that you solve this ODE by some linear multistep method or Runge-Kutta method. It can be an A-stable would certainly work, but in fact, for our problems, you can use A-alpha stable. Yeah, so first, certainly for Runge-Kutta methods, there's no limit on the order, and some limit on the linear multistep method as described by Dahlquist's barriers. Okay, and then once you solve this by an ODE solver, you plug that back into this formula, and you get the numerical approximation of u. Okay, this doesn't explain how to implement this, but that's a method. So let's look at it with one particular ODE solver, namely the backward Euler discretization. Okay, so I discretize this simple ODE by backward Euler discretization, and then I can write the solution of it directly. And in fact, it's given by a discrete variation of constants formula. So this R is the stability function of the backward Euler discretization. We see that it's A-stable because it's less than 1 when real part of Z is negative. Yeah, so it will be stable. And you see that here this continuous convolution in the continuous variation of constants formula has been replaced by a discrete convolution. And now we plug this back in. Yeah? You plug this back into that formula there. So you see the only thing that depends on S are these R's. Yeah? So you plug that in here, and then you have to, you can take the evaluation of G at equal time steps Dj out, and you get that you get a discrete convolution for the solution UN with weights omega, where the weight omega is this integral over the data, over the kernel K, and these powers of the stability function. And you see, this is a kind of a discrete inverse Laplace transform because we know that the stability function is approximating e to the z. Yeah, so this is approximating e to the tj times s, or tj plus 1. Okay. So this is a method. Of course, we can use, and in fact, I was going to say for the fractional derivative or integral at least, this is the Grunwald-Letnikov formula with the backward Euler. But of course, we can do. This is really just for illustration purposes. We can do high orders, and we do high orders. Okay. That's fine, but you see, what we all encounter with non-local operators is that now we have a discretization, but usually you would like to compute this un now at capital N points, and just using this formula, that would take order n squared time. Yeah, because at each step you need little n evaluations, and then in total it's n squared. Of course, things can be sped up by FFT schemes. They are well known, certainly in the CQ, within the CQ framework from the beginning. But we want to do something different. So let's do something else. Yeah. So let's see what if we can do a very efficient discretization of this integral here. Okay. Let's suppose we can. Okay. So then we would get a quadrature formula like this. So we have to evaluate the kernel at some frequencies sk and the stability function at some frequencies sk delta t. And let's assume that the number of quadrature points is low. Yeah, say order log n. Okay, great. Then we plug this back into the formula. Yeah, and for each sk we have a discrete convolution. Yeah, which can be easily updated just in one step. Okay. Now, there's another way to say that, and maybe I should have really done that, and that's that you do first. You don't do the CQ first, but you first do the quadrature in the Laplace, the inverse Laplace transform, yeah, and that means then what you're left with are NQ ODEs to solve, yeah, and they are local. The fractional derivative has disappeared, so the update is local and doesn't cost any memory. Okay, so you see the only thing you have to store are these q and k's. Yeah, at time point tn, you only have to solve these q and k's, and there are k equal to 1 to nq of them, and if nq is order log n, then that means that at each time step we need log n calculations. And only log n memory. Yeah, with FFT schemes, you can do order n log n computational time, but here we also use the memory and active memory to order log n. Okay, so that's wonderful. Yeah, so that's very simple, and this is known as the fast and oblivious quadrature due to Christian Lubich, Achim Scheele, and Maria Lopez Fernandez. However, there are some issues. So in that ideal world that I presented on the previous slide. So the usual approach, and you have seen it in Graph and Stoke on Monday, I guess, is to take a hyperbola or a Talbot contour that extends to the left half plane, where this e to the st decays exponentially, and then apply a trapezoidal quadrature rule. Yeah, this is excellent. This works exponentially fast. There were many people involved in this work, and what's the work? Well, the work is to choose this hyperbola or Talbot contour or something else very carefully, optimally, and choose the quadrature in an optimal way. Yeah, and this works very well if you want to compute this inverse Laplace transform at a single time t. Okay. The problem is that we really want it to work for all times t. And there are many different scales, and this is, well, maybe I'll go back to here to explain that, yeah, because you see, here this r behaves like e to the z, yeah, and I will change this contour to the right half plane, yeah, so this z has then a negative real part, and it has a very quick decay. Yeah? But it's being multiplied by delta t times j, so tj. Yeah? So if tj is large, this exponential decay is very fast. Yeah? So you need to cut off the integral quickly and have many points close to the origin. If the tj is close to 0, well, the decay is slow. Yeah? So you have to go far away and solve your quadrature points in a different way. So this is not easy. Yeah? And the solution by Achim, Maria, and Christian was to do the first few weights directly. Yeah? So when t is very close to 0, you have very little decay, so you do them just in standard CQ schemes. And then have split time into fast increasing intervals, exponentially increasing. And for each one time interval, you're able to choose an optimal hyperbola for each of these log n intervals. Yeah? And they have only a few quadrature poles. Okay? So this actually works very well. And this is a well-known algorithm. So you might ask, well, why am I revisiting it? And the reason is, and Maria has more experience with this, of course, and she tells me certainly that the complexity, the requirements are met, but the complexity of the algorithm itself is quite high. Yeah? By complexity, I mean complexity of implementation. Yeah? Especially if you want to do adaptive schemes. Yeah? You can do adaptive schemes. You just do this ODE solver can be adaptive. But that requires really ingenious complex data management, which is difficult to implement. And if you've been implementing kind of fast schemes, simplicity is important, yeah, because that generally, as a rule of thumb, makes the constant in these order notations small. So we thought with Maria that let's do something special for this very important but limited case of the fractional integral. Okay. Sorry. So this is just a very quick detour, which I could have skipped, but just to show you the form of it. So I said that we can do high-order linear multi-step method, and there I will need a bit more time to explain how to do that. But for A-stable Runge-Kutta methods, it looks really like backward Euler. Backward Euler, you can view it as a Runge-Kutta method with one stage. So an M-stage Runge-Kutta method is a one-step method, but with M stages. So it all looks very similar to the backward Euler scheme, but here you don't have just this stability function R, but a slightly more complicated thing where R is still there, this power of R, but you also have a vector here of the Q, which is of the size of the number of stages. So the implementation gets a little bit more technical, and you have to evaluate the data not just at equal time steps, but also at the stage in between. But this is what we did the full analysis for. Okay. So we can do high order, but just keep in mind the backward Euler case. Okay, so let's look at now, that was in the general CQ, now let's look at the fractional integral. So where the scale of s is s to the minus alpha. Okay, and now, so I don't I like to wave my hands, which is difficult here, but we started with this Bromwich contour, which is parallel to the imaginary axis, but we deform it to the left half plane. And not just to kind of a hyperbola that's, that always has a positive, well, non-zero imaginary part, but we let the two parts of the contour approach the negative real axis. Yeah? So this is where this z of s to the minus alpha has a branch cut, but that's perfectly fine. In fact, the part that has a jump along the branch cut cancels. Yeah? Or you can, that then nicely gives you a real formula. So it's no longer complex numbers here. It's an integral over the negative real axis, or I change the variables to numbers on the positive real axis. Okay, and now it's a very simple integral now. Let's see. So it still has these multi-scales. Yeah. So one issue that we have is that it has a singularity at 0, but that's not really an issue because it's the usual weight x to the minus alpha, which we can deal with in with Cauchy quadrature. But then we have this En, where remember En is like the stability function R, and En of z approximates e to the nz. Yeah. So here you can think of this being e to the minus Tns. Okay. So again, if Tn is small, there's little decay. If Tn is large, there's very fast exponential decay. Okay. But we fix the contour. Okay. And yes, and I should say that this is really compare this with the real inverse Laplace transform, very nicely described in Henrich's Bible, three-volume Bible on computational complex analysis. Okay. So, and now what we do is we truncate, of course, and we truncate so that it's valid for all times, even the low times. Yeah? So we go all the way to all the 1 over delta t. Yeah? And then, now this is where we take geometrically increasing intervals. Okay? So there will be only order log n of them. Yeah? And in the first interval, we do a Cauchy quadrature, which can deal with this, has this weight already. Yeah? So there's an exponential decay of the error of the quadrature, and it's based on the size of the Bernstein ellipse that you can choose around this interval. And this Bernstein ellipse will then go into the other half of the complex plane, where you will have an exponential increase of this e. So we can't make this first interval too large. In fact, we choose it as 1 over the final time. Okay. And then in these increasing intervals, you do the analysis in the same way. You have exponential decrease because everything is analytic, as long as the Bernstein ellipse is not too large. Yeah, and we can arrange it so that the convergence is similar in all these intervals. This is why you choose this kind of exponential increase of the intervals. And finally, what you get is that in each of these log n intervals, for a fixed accuracy, you only need a fixed number of quadrature points. Yeah, these. And so the total number of quadrature points is the number of intervals, which is log n, times log of the tolerance. Okay, so our number of quadrature points is log n times log tolerance. Yeah? We also do first few weights directly, but that doesn't change the complexity. So there it is. We managed to do what we wanted to have in that kind of what I call the ideal world. Okay, and now let's look at just some numbers, because that's what's really important in the end. Yeah, that it really does work well. So here is the fractional integral with alpha equal to half, backward Euler on the left, two-stage run-out 2a on the right. Various choice of parameters, but the main important one is that the tolerance of the accuracy of this oblivious quadrature is 10 to the minus 6. And we see that it's not growing very strongly with the delta t. This is logarithmic growth, very slow. Not growing very fast with the final time. Yeah? And you see, so for example, here, for what is it, 10 to the 7 weights, yeah, 10 to the 7 points, we really, in some sense, reduce that to 48. Yeah? So it's a huge change. Similarly for the run-out 2a. Okay, then some further data where we look at for different fractional powers, and no great issue there. It seems to be, work a little bit better when we are closer to alpha equal to 1, but it's very similar. Okay. Yeah, so low alpha and high accuracy requires a bit more, but that's okay. And this is just a plot to show that the tolerance is, well, this is an important plot, that the tolerance is more or less constant over all times n. Yeah? So that means that we really are close to optimal choice of the number of quadrature points. Yeah? That we are not doing too much for some choice span. Okay. Clearly a bit here could be improved, yeah? Because the largest error is just in these first few, but then it becomes very stable. Okay, but that's the first part. of my talk. And now let's look at a couple of examples. So here's the subdiffusion, diffusion wave equation, and here, as we have heard in the first talk of the conference, it's very important that these kind of problems have a singularity at t equal to 0. But in this example, I will ignore that, because I only care about the fast computation of the history. But I will come back to that with my next example. So here I'm just taking 0 initial data, and I give here a convergence result, but it's using standard CQ theory, so I don't want to dwell on it much. What I really want to show, maybe just how do you implement this. Well, okay, so this beta, I allow it to be between 0 and 2, okay? So what we first do, we do with the underlying discretization of the derivative, we do m classical derivatives, that creates a new variable b, which we apply to the CQ, the convolutional quadrature. Yeah? And then at each time step, did I write that? I didn't, but unfortunately, yeah, so at each time step, this is what we solve, and you see this Vn will contain Un, so what you have to invert is the stiffness matrix plus and here I'm just for simplicity to shorten the notation, I'm assuming that the mass matrix is identity. Of course, in practice it's not, but it's here what we have to invert is the shifted Laplacian, so the stiffness matrix plus a positive number times the mass matrix or something like multiply will work very well. Okay. But this is the main point, that here is a 2D example, and I compare the standard error, the error with the standard CQ as a decrease as a decrease time step, and the error with the new implementation, really I should say, yeah, and compare the memory. Yeah, and of course the error is preserved, but the memory is growing only very slowly. With the new scheme logarithmically, whereas with the standard memory, it's growing very fast, of course, linearly. Yeah. And of course, in 3D, there will be no comparison. Now, very briefly, of course, this is just for the fractional integral, but we can do much more complicated operators. So we could instead directly write U as the convolution of the data of the right-hand side F with a kernel little k whose Laplace transform is this resolvent. Yeah? In fact, and then again you can transform the contour to the left half plane because it's the sectorial operator. And here I did something that's not allowed. Well, this is allowed. I can again make the contour just a negative real axis. Yeah? But I don't know, I can't deal with the singularities easily with Quadrature Formula in the first interval, so I just did Gauss quadrature there. Okay? We have better and more rigorous schemes than that, but here, and nevertheless, I think this is an interesting example, because what I'm able to do here is to compare it with the standard CQ implementation using the Toplic structure, as we've seen before, which is very fast. It's order n log n, but it requires order n evaluations of the kernel k, which is now this resolvent, which is not easy to compute, and requires the order n memory. Yeah? And now I compare it with our method. We get the same accuracy. Of course, much better memory, but I don't show that here. But what was very interesting to me is that even very quickly, the timings are better with the new method. Yeah, the complexity is the same. It's order n log n for both. But because it's such a simple algorithm and doesn't need so many calculations of k, it's already faster. Okay, so how much time do I have? Oh, I'm okay. I'm okay. So let's go to the main example that I was interested in. So this is the model problem some called Salvo's equation, or Chen and Holm introduced it with a Caputo derivative here. So again, this is the D'Alembert operator. I set the wave speed to 1 just to make it simpler. And this term here is there to attenuate the wave, to damp the wave. Yeah? So if gamma is 0, this is the standard damped wave equation. Okay. It's important in actually nonlinear acoustics with applications to high intensity focused ultrasound. But as I said, for us here, only the linear part is of interest. And gamma depends on the tissue. Yeah? It's here for us it's between -1 and 1, but in fact the regime with gamma greater than 1 is of interest in applications. But there I would rather use a strong damping where we have a weaker fractional derivative in type, but we have a Laplace U. Okay, but I won't address that here, though we have results of that as well. Okay, so what does this term do? Well, it's well known. I mean, this is why it's being used, that this term attenuates the energy. So this result is certainly not due to us, but I think the constant might be a bit new. So let's read it. So it says that when you test the time derivative, so you see this is now the Riemann-Liouville derivative. The time derivative of the fractional integral of g with the g, then this is positive and bounded below by the expression on the right, and especially importantly for us, the integral, the fractional integral of f tested with f is also bounded below. Yeah. And these results have been available before, but with slightly different constants. In particular, in Bill McLean's paper 2012 in the appendix, I think our constant is slightly better. And essentially the same proof is, well, we used the proofs from the PhD thesis of Shishkova. And in fact, how I first got to this constant was reading one of the original papers on the L1 scheme. So this is and there's a nice proof of stability of the L1 scheme, which essentially proves I don't remember which one, well, I guess the first one of these results in a discrete sense. Yeah? So the L1 scheme satisfies this, the discretized version. But I won't be using L1 scheme here. Anyway, so as usual, to analyze the wave equation, you test with the time derivative of u. You have the energy, which is a combination of the kinetic and potential energy. And let me just describe it for the simpler case where gamma is negative, -1 to 0. Yeah? Then we have, in the usual way, if the right-hand side is 0, if there are no sources, we have the time derivative of the energy plus this term is equal to 0. So integrating in time, we have that the energy at time t is the initial energy minus this integral. And yes, so remember the gamma is negative. Yeah. So in fact, this fractional, remember we had the fractional derivative of all the gamma plus 1. Yeah. So it's Caputo. So first take the usual derivative, and then I have this fractional derivative of order minus gamma, which is really the fractional integral. The fractional derivative of order gamma, but gamma negative. So this is the fractional integral of order minus gamma. Yeah. And from the previous result, we see that this term really reduces the energy. Okay, and now for the discrete scheme, we want the discrete scheme to have this property as well. Okay, so that it's stable and we can analyze it. Okay, but first, what do we know about the solutions of this problem? So for gamma between -1 and 0, it's just like for the wave equation. If the initial data is in H1, sorry, I don't remember if I said it, my boundary data is homogeneous, so the initial data is H1, 0, the time derivative of u at 0 is L2, and if f is in L2, L2, then we have the usual smoothness of u, so that, for example, the second time derivative of u is in L infinity in time, but in the dual space of H1. In omega. Now for gamma between 0 and 1, we somehow needed stronger assumptions on the initial data, and then we get the same smoothness of the solution. It's obtained by differentiating the original equation. And there's just as we submitted this paper to IMA, JNA, and Rashuli told us that they had recently published a paper on the fractional Zener equation where they had similar results. Okay. So what do we do in the discrete case? Now, the discrete, the CQ approximation of the fractional integral, we can actually write it, while we don't use it that way, we can write it at every time point t, and we can take its Laplace transform. And then what we see is that the action of CQ is really just to replace s to the minus alpha with some approximation of s to minus alpha. Okay. For backward Euler, this approximation would be this expression. And you can see that this is that for real s greater than 0, real s of delta t is greater than 0. So we have stability, and it's analytic also. So in particular, this can be used by using Parseval's formula, by going to the Laplace domain, to show that this kind of positivity property of the continuous case is conserved by the CQ. Okay, so doing CQ there, we can really still have that stability in the discrete case as well. So here the gamma is between -1 and 1. But remember we had gamma plus 1. Yeah. So, but of course we test by the time derivative of u and apply to the time derivative of u. This will be important later. In fact, here. So here's the scheme. Okay. So let's first forget the fractional derivative. So avoiding if the fractional derivative were not there, it's just the leapfrog scheme or the Newmark scheme. So the centered second order approximation of the second derivative. Here, the stiffness matrix is just applied to un. To shorten the equations, I'm assuming that the mass matrix is identity, but of course it's not in practice. Okay, and then for the fractional derivative, we had here gamma plus 1. So instead, what we do, we first apply the centered difference derivative to u, yeah, and then we apply CQ to the order gamma derivative. Yeah, so we can use this positivity here. Okay, and if you know this, going all the way back to the CFL paper, how to analyze this scheme is to test exactly with this Vn. Yeah, so this is why this is perfect that I have the V here. Now CQ is really made for the Riemann-Liouville derivative. Yeah, so when gamma is greater than 1, we need to do a correction that we subtract the initial V0 here. Okay, this basically makes this CQ exact for constants, yeah, because the Caputo derivative of a constant is 0, yeah, whereas the Riemann-Liouville is not. So I'll have these correction terms later as well. Okay, and then we solve by explicit time stepping, and at each time step you just need to invert the mass matrix, or if you're using mass lumping, it's diagonal or something else. Okay, and for the history, we use the fast method. And then, as I said, we mimic the continuous case, test with Vn, and we have stability, Gronval, etc. Yeah. Okay. Now, I kind of brushed under the carpet in the previous example the singularity at t equal to 0, but I won't do it here. So now we do know that u is twice continuously differentiable, yeah? But once you go to higher derivatives, you don't expect to be bounded at t equal to 0. Okay, so what's looking at the after spatial discretization, looking at the Volterra integral equation, what is the correct behavior is and correct assumption, I believe, is the following on the smoothness of the solution, and that's that u is in C2, okay, and we assume that this is in H1 in space, and that u is in C4. Yeah, so be careful here, the C2 is on the closed time interval. It's in C4 on the open time interval at 0, yeah, and the derivatives behave as follows, yeah. So you see this alpha will be great between 0 and 1. So up to k equal to 2, everything is bounded, but already at k equal to 3, the derivative might be unbounded at t equal to 0, unless this ck is 0. Okay. And this alpha, depending on gamma, is as follows, but in any case, I guess alpha is always between 0 and 1. Yes. Okay. So this is, I believe, the correct assumption. And under this correct assumption, we have the following error estimate. which is very long, but let me kind of lead you through it. So it's the standard analysis of the wave equation. We compare the discrete solution with the elliptic projection of the exact solution. So RH is the elliptic projection. Here we have the energy norm in, well, not the energy norm, well, it's the time derivative of u in L2 in space and u in L2 in space. Yeah? And you see we have in space these kind of errors in L2. So if you're using piecewise linears and u is smooth enough in space, you will get h squared. Yeah? So we get optimal error estimates in space there. Epsilon h is just an h error, so the spatial mesh width error, which has a similar form like this, but with various derivatives of u. Then we do have a restriction of the error to delta t to the 1 plus alpha, unless these C3 and C4 are 0, yeah, unless the solution is smooth. Otherwise, it's delta t squared. And in the higher norm, we just have the h1 norm here, so we'll just get h in space. But there's this term a gamma, which is important, and here it is. So for gamma between -1 and 0, it's only delta t, and for gamma between 0 and 1, it's delta t to the 2 minus gamma. So interestingly, it's better than for gamma between 0 and 1. But the reason that it's better for gamma between 0 and 1 is because there we had already done a correction term, this subtraction of v0, which makes the CQ fractional derivative exact for constants. And if you add further correction terms, you can make this a gamma disappear. And we do that. Yeah? So we don't have this restriction, but the only restriction is this 1 plus alpha. Okay, so between 1 and 2. Yeah, unless the u is completely smooth. Okay, so let me then conclude, I think, with some numerical results. Okay, so here's the, we have many numerical results, but I decided to show just a single one in 1D. There will be a 2D example as well. Okay, so it's this Salvos equation. I have a constant here, a gamma, that also depends on gamma. It actually blows up with gamma at the integer points. So yeah, we certainly always assume that gamma is not integer. Yeah, there, other things would be done. Okay, we have some right-hand side f, initial data u0, v0, and as always, 0 boundary condition on omega. And here, yeah, well, here it's just the interval 0, 1 or -1, 1. I'm not sure which one. Okay, I could either, put a smooth f, but we have an exact solution. We just plugged in an exact solution that has the kind of singular behavior that we expect. Okay, yeah, and that produces an f, which we then use to run our scheme. Okay. And so, a bit embarrassingly, in the last minute I couldn't find the images, so I just print screened the image from our paper. So these are the results for different gammas, for the negative and positive ones, and with the correction terms and with no correction terms. So let's look at the negative gamma first. So without the correction terms, we always expect just order h. So this is this blue dashed line. Yeah? And indeed, the numerical experiments show exactly that. Yeah? So we know there are no miracles, that's what we get. But the correction terms should, now this is very difficult to read, but should lead to, yes, well, we know, I know, it should be 1 plus alpha, and in this case, alpha is minus gamma, so this should be 1.75, and indeed we get something like that. Yeah, it looks possibly a bit better, but so I don't know if Katie is here, maybe not, but I think this is why also I kept that constant a gamma there. If you increase it, then the effect of the fractional derivative is stronger, and you can earlier see the the effect of it, so you do see this 1.75. And that reminds me that actually I glossed over one thing. Maybe I should go back to that. So why am I getting second order? Sorry, I forgot to say that. Which convolution quadrature I'm using? I'm actually using a convolution quadrature I didn't describe. And that's the second order backward Euler scheme. Not backward Euler, backward difference formula. Yeah. So this is an A-stable method. And I did describe the scheme because if you go back all the way to the beginning to my description of CQ, I just solved that ODE with a BDF tool. Yeah. So this can be done. Okay, and the fast method can be implemented for this as well. Okay. Anyway, so this is why second order is the best we can expect. So here, with gamma equal to minus 0.25, so perhaps surprisingly, this is where we expect, even with the correction, a lower order convergence, because it's 1 plus 0.25, so 125. And initially, so this took us some time because you see, initially it looks wonderful, it's second order. Yeah, but in fact, what's happening that it's just you don't see the singularity immediately. Yeah, and eventually it really settles exactly to 1.25, seeing that our theory is sharp there. Okay. Then with gamma positive, this is where we. Where, again, perhaps surprisingly, closer to gamma equal to 1, things are better because of, so here, or is that right? No, closer to 0. Then, yeah, I think this is 1.75. And here, here both the no correct, okay, yeah, so here both with the inverted commas, no corrections, and corrections we expect the same, and we get the same. But remember that for gamma positive, we are by default doing this one correction term, the subtraction of V0, in order to have a Caputo derivative and not Riemann dual. And here, again, we expect the same with no correction and correction, but and with no correction, we do see a worse behavior than with the corrected scheme. Okay, but perhaps even more importantly, with I should be finishing with respect to this talk, is how's the memory doing and the timings. And this is a 2D example, and we see a very slow increase in memory. Well, no, sorry, this is a very slow increase in memory when we increase the tolerance, yeah? But compared to the standard FFT CQ, it's enough to keep this at tolerance 10 to the minus 5, so we have 8 megabytes of memory instead of 200 megabytes, yeah? And even the timing is better, yeah? So it really works well, okay? So my conclusion is that it's a simplified oblivious quadrature for this fractional integral, yeah? It's an important operator, so it's important to do something special for it, yeah? And it is for the tried and tested CQ's fractional calculus, yeah? So we haven't changed that, it's just an implementation. I believe that our results for the damped acoustics are very nice. And in fact, ideas are applicable much more broadly, yeah? So to any, and we are working on that now for general sectorial operators. But in fact, I like the talk by Garapa on Monday very much because this fractional derivative, variable fractional derivative would fit in this framework completely, and might even, depending on this A of S, might even be possible to do really this real integral. Yeah, so that would be interesting to look at. So most of what I've talked about has been published. So the paper with Maria on the fast fractional integral is in Numerische Mathematik. And the work with Katie on the rest of it has been accepted in IMA JNA, but is on archive. And there's a book coming up, albeit on a different topic, on time domain integral equations, but there will be a chapter on parabolic problems which will contain some of these codes as well, and some descriptions. Okay, so I believe I should really have finished. Yeah, sorry about that. So that's all I wanted to say.
Okay. Thank you very much to our speakers, Professor Banjai. Are there some questions from here or from Zoom? Okay. No, you're coming. Okay.
Okay, thank you for this very nice interesting talk. Can you hear me?
Yes, I can hear you. I can hear you well.
I have just a curiosity, very general curiosity.
I don't know if you are aware
or another family of methods, the kernel compression scheme, which in the beginning they seem to be developed in a similar way as you developed these rules. Actually, by some working the non-local problem in a family of local problems. But actually they are different. My question is foreign. Maybe is there any connection to big families of methods? Usually I don't expect an answer, but just a comment maybe. I don't know if you are aware of this kernel compression scheme.
Okay. I wasn't sure which method you mean. So do you mean the kind of works stemming from fast multiple hierarchical matrices community?
Yes, maybe.
Yes. So in fact, there's a very recent archive paper. I didn't mention it much because I haven't yet managed to read the details of it. So certainly, this is the kind of kernel that has been analyzed, and can be dealt with these schemes. And there's a recent paper that actually describes oblivious quadrature in that language. Okay, and what's very interesting is because so in the H matrix community, there's the H matrix family of methods and the H2 matrix family of methods, with the latter being more similar to fast multiple methods. And one difference between them is the H2 can remove the log n. Yeah, so this might be a possibility to remove this log n in the n log n. Okay.
Yes, maybe we will discuss it during coffee break, but
Okay,
you
sure.
will not attend our coffee break.
Yeah,
Thank you for your
I can be virtually there.
Yes. Thank you very much for accepting the invitation.
No, thank you for inviting me. Yeah.
Okay. Are there some other questions?
We have a comment from Kamal. He says, thanks for presentation, it's very interesting. So thank you, Kamal.
Thank you.
Okay, thank you again, our speaker. There is a question. Okay, sorry. Okay, no, thank you again for your interesting talk. And look. Okay, now it is time for our next talk by Francesca Soldi from the University of Rome, La Sapienza. We will speak about, our numerical solution of fractional differential equations by slightly operators.
Vogliamo usare subito di tutto che sta sulla concina intanto perché nessun altro
Okay, now we stop with the YouTube and for today.
Sì, salutiamo.
For today, so thank you for attending our conference from home, and thank you very much again for our next speaker.
Ok, sì, devi condividere.